LLM, token, context, prompt, tool, MCP, agent, agent skill. You've probably heard all of these terms. But here's a question. Can you actually explain what every single one of them means? In this video, we're skipping the fluffy business jargon. We're coming at this from the lowest level engineering view and breaking each concept down piece by piece. By the end of this video, your understanding of AI will level up. Let's start from the very bottom and build our way up, layer by layer. At the very bottom sits LLM. It stands for Large Language Model. We just call it the model for short. Pretty much every large language model today is built on top of the transformer architecture. The transformer architecture was first proposed by a team at Google. The paper is called Attention is All You Need. Here's the dramatic part. Google lit the match, but it was OpenAI that poured gasoline on it and set the whole world on fire. Right after that, GPT-3.5 dropped out of nowhere. It was the first model that was actually usable in the real world. Just a few months later, GPT-4 launched. It pushed the ceiling of what AI could do to a whole new level. Honestly, the GPT family is basically the crew that kicked off the entire AI wave we're living through. Even today, GPT is incredibly powerful. The latest, GPT-5.4, is one of the benchmarks for the entire industry. But the AI race hasn't been an OpenAI solo for a long time now. Players like Claude and Gemini have stepped up, and they're competing head-to-head in the areas where they're strongest. All right, we've covered the backstory of LLMs. So how do these things actually work? It's surprisingly simple. It's just a word completion game. Let's look at a concrete example. Suppose you ask the model, "Is it sunny today?" The model takes your question, runs it through a bunch of internal math, and predicts the next most likely word. Yes, it is. Here's the key thing. After the model spits out, "Yes, it is," it doesn't stop. It grabs "Yes, it is" and appends it to the end of your input. Then it takes that new input and predicts the next word. Say sunny. Sunny also gets appended to the end of the input. Next, it takes the expanded input and predicts again, today. It appends today to the input. At that point, the model decides it's done talking and outputs a special end-of-sequence marker. Just like that, we have the model's full answer. Yes, it is, sunny, today. That's the deepest layer of how an LLM generates text. Once you get this, you'll understand why these models output one word at a time. But here's the thing, large language models don't actually read text. Under the hood, an LLM is just a giant math function running nothing but matrix operations. It takes numbers in and spits numbers out. It doesn't read human-written text at all. So how do we bridge the gap? We still need a translator between us and the model that's the tokenizer. Here's a concrete example. Suppose the user asks, "What did you think of Alex's latest video?" Step 1. Split. The tokenizer breaks this sentence into the smallest chunks it can. Each chunk is called a token. In this case, it produces 4 tokens: Alex's, latest video, and what did you think of? Then the model outputs a token ID, for example, 4,821. The tokenizer then translates that 4,821 back into text, say, Alex's. That's the decoding step. You might be thinking, so a token is just a word, right? Not exactly. Take programmer. That has to be one word, right? But the tokenizer splits it into 2 tokens, program and mer. Same thing in English. The word helpful gets split into 2 tokens, help and full. Even the checkmark symbol takes 3 tokens to represent. So words and tokens don't have a strict one-to-one mapping. A token is just a chunking rule the model learned on its own. On average, 1 token is roughly 0.75 English words, or about 1.5 to 2 Chinese characters. For example, 400,000 tokens is roughly 600 to 800,000 Chinese characters, or about 300,000 English words. All right, we've talked about tokens, the basic unit the model uses to handle text. Let's look at something you've probably taken for granted but is actually worth thinking about. When you chat with an AI, it sometimes feels like it remembers your earlier conversation. For example, if you open with, "My name is Alex," then later ask, "What's my name?" the AI still gets it right. But here's the catch. An LLM is just a math function. You give it input, it gives you output. It doesn't have real memory like a person does. So how does it actually remember earlier chat content? The answer is, every time you send the model a message, it isn't just your latest message that gets sent. The app behind the scenes grabs the entire conversation history and ships it along. That way, with your question and the full history, what the model sees on each turn is the complete conversation. That's how it knows what happened before. Which brings us to context. Context represents the total body of information the model receives each time it handles a task. Your question and the chat history are both parts of context. On top of those, there's the tokens the model is currently generating, the list of available tools, the system prompt, and more. You can think of context as the model's short-term memory. Once you understand context, the next question naturally follows. How big can context get? That's where context window comes in. For example, GPT 5.4 has a context window of about 1.05 million tokens. Gemini 3.1 Pro is 1 million. Claude Opus 4.6 is also 1 million. We said earlier that one token is about 1.5 Chinese characters. So 1 million tokens is roughly 1.5 million Chinese characters, enough to fit the entire Harry Potter series. Alright, suppose you have a 1,000-page company product manual. You want the model to answer customer questions using that manual. How would you do it? That's where RAG comes in. Suppose you have a 1,000-page company product manual, and you want the model to answer any customer question using it. How would you do it? Just dump the entire manual into the prompt along with the user's question? That's not a great plan. That's where RAG comes in. RAG can pull out the chunks from the manual that best match the user's question. It sends just those chunks to the model, so the model answers based only on those snippets. Instead of a whole book, the model might just see a few paragraphs. No more context window limit, and the cost drops a lot. If you're interested in RAG and want to dive into how it actually works, check out my other video. Prompt. It's the specific question or instruction you hand to the model. For example, if you say, "Write me a poem," that sentence is the prompt. Don't overthink prompts. They're just questions or instructions you give to the model. But there's a problem. If you just say, "Write me a poem," the model might write a Shakespearean sonnet or a free verse poem or even a limerick. Why? Because your prompt is too vague. The model has no idea what you actually want. So how you write your prompt directly determines the quality of the output. A good prompt is clear, specific, and unambiguous. For example, "Write me a Shakespearean sonnet. Theme is autumn leaves falling. Style a little melancholic." Now the model knows exactly what you want, and the output is much closer to what you expected. That's why there's a whole field called prompt engineering. It's basically studying how to say things clearly so the model understands your intent. This used to be a hot topic, but you rarely hear people talking about it anymore. Low bar to entry, and models keep getting smarter. Alright, you've got the basics of prompt down, but there's still more. Have you ever thought about the fact that sometimes we need to tell the model not just the task, but also a persona and rules of behavior? That brings us to two different prompts. The one describing the actual task is the user prompt typed in by the user. The one describing the persona and the rules is the system prompt configured by the developer in the backend. Let's walk through a concrete example. Suppose you're building a math tutor bot. You want it to guide students through the problem instead of just giving the answer. You need both prompts. First, the system prompt. In the backend, you set it like this. You are a patient math tutor. Then the student types, "What is 3 plus 5 in the chat?" That's the second prompt, the user prompt. The model sees both prompts, and it knows it has to act as a guiding tutor. It answers like this. Let's think about it this way. You've got 3 apples, then someone gives you 5 more. How many do you have now? See the difference? Without the system prompt, the model would just say 8. But with the system prompt's constraint, the answer is completely different. With user prompt and system prompt working together, The model can follow the rules and still handle the actual task. That's it for prompt. Alright, that's it for prompt. Let's move on to the next concept, tool. First, a weakness of large language models. They can't sense the outside world. For example, you ask the model, "What's the weather like today in San Francisco?" It says, "Sorry, I can't get real-time weather info. My knowledge cuts off at some past date." Why? Because the model is just a word completion game. It really has no way to hit a weather website and pull real-time data. A tool is essentially just a function. You give it input, you get output. For example, a weather lookup tool takes two parameters, city and date, and returns the weather info. Let's walk through the full flow from a user asking a question to the model answering. There are four actors: the user, the model, the tool, and the platform. Step 1. The user's question goes to the platform first. Step 2. The platform forwards the user's question to the model, along with a list of available tools. The model looks at all this and thinks, the user wants the weather. I don't have real-time data, but there's a weather tool got it. I'll call it. Step 3. The model generates a call instruction with the tool name and parameters and sends it to the platform. Step 4. The platform receives the instruction and actually calls the tool, which is just running the function behind it. Step 5. When the tool finishes, it sends the weather JSON back to the platform. Step 6. The platform hands that result over to the model. The model takes the data and turns it into a sentence. Today in San Francisco, it's nice and sunny, 52 to 65 degrees. Step 7. The platform forwards that sentence to the user. Every actor has its own job. The model picks the tool and summarizes. The tool runs the lookup. The platform orchestrates everything. Important, it's the platform that actually calls the tool, not the model. The model can only output text. All the model can do is output text saying which tool it wants to call. It can't actually run a function. To summarize, a tool gives the model a set of external capabilities it can call on. But there's a big headache with tool integration. Let's talk about MCP. But there's a big headache with tool integration. Look at these three platforms: ChatGPT, Claude, Gemini. Each platform has a different integration spec. So you write the same tool 3 times because every platform's technical standard is different. Someone in the AI world had an idea. What if there were a single universal standard? That's where MCP comes from. MCP stands for Model Context Protocol. The name's a bit academic. Just think of it as one universal technical standard for plugging tools in. With MCP, a developer builds a tool once, following the MCP spec, and that tool works on every platform that supports MCP. It's like every phone now using USB-C. One universal standard, everyone's life gets easier. A developer writes the tool once for the MCP spec, and every supporting platform can use it. If you want a deeper dive into the MCP protocol, check out my Ultimate Guide to MCP series. Logically, with tool and MCP, the model should be unstoppable by now. But actually, it's still missing one thing. Let's throw a harder question at it. What's the weather like here today? And if it's raining, can you find an umbrella shop nearby? Suppose we have these tools available: a location tool that grabs the user's coordinates, a weather tool that takes coordinates and returns the forecast, and a shop tool that takes coordinates and finds nearby stores. The model thinks, the user wants the weather. To get that, I need to know where they are. There's a location tool. Let me call it. Got the location. Next, I need the weather for that spot. There's a weather tool. Call it. It's raining. Per the user's request, I also need to find an umbrella shop. There's a shop. Tool call it. Search for umbrellas. The model pulls it all together. Every goal is met. Time to give the user the final answer. You can see this isn't a single tool call anymore. It's a chain of multiple operations. Earlier in the tool chapter, it was one call. Now the model is planning on its own and making multiple calls. We call a system that can plan on its own, call tools on its own, and keep going until the task is done: an agent. An agent has 3 core capabilities: plan on its own, call tools on its own, and keep running until done. Today, the popular agent products out there include Claude Code, Codex, and Gemini CLI. The architecture patterns they use vary a lot. Classic ones include react and plan and execute. Agents are awesome, but there's a new pain point. Next chapter, agent skill. When you start using agents a lot, you'll quickly hit a new pain point. Every time you head out, you have to copy-paste a giant blob of rules into the prompt. All your rules, your format requirements, even examples copy-pasted into the prompt and sent over. Imagine having to type out that giant list every time you leave the house. That's pretty unreasonable, right? Don't worry, this is exactly where agent skill comes in. An agent skill is essentially a specification document you write ahead of time and hand to the agent. It's just a markdown document. The overall structure splits into two parts, a metadata layer and an instruction layer. The top part is called the metadata layer, basically the cover page of the spec. It needs at least two properties, name and description. The name is the identifier of the skill. Ours is called Go Out Checklist. From goal to the end of the document, all of that is the instruction layer. The instruction layer has no specific format requirement. In the execution steps, we tell the agent, first call the location tool to get coordinates, then call the weather tool to get the forecast. Decision rules. Rain means umbrella. Strong sun means hat. Bad air quality means mask. Windy means windbreaker. Output format. Start with a one-sentence summary, then list each item with its reason. Once defined, you need to save it in the right place on disk. Taking Claude Code as an example, you need to find the Claude Skills folder under your home directory. 2 rules for storing. First, the folder name must match the skill's name exactly. Second, the file must be named skill, MD, with skill in uppercase. Once saved, open any empty folder and launch Claude Code. During startup, Claude Code will notice there's a new agent skill in the skills folder. It reads the metadata, the name and description from the skill.md file. It doesn't read the instruction layer yet. Claude Code only reads the instruction layer when it decides the user's question is related to that agent skill. Type in the question, I'm about to head out. Tell me what to bring. Claude Code starts working. First, it asks to call the location tool we approve. Then it calls the weather tool we approve again. After getting everything it needs, Claude Code formats the answer the way the skill requires. Yep, that's basically all an agent skill is. Just a document, a specification document for the agent to read. An agent skill is just a markdown specification document for the agent. It mainly locks in the steps and rules for getting things done. Of course, agent skills have advanced features too, like running code, referencing resources, and so on. The progressive disclosure loading mechanism is also a major feature. It saves a lot of tokens. Alright, that's all the concepts. Let's recap the whole framework. LLM stands for Large Language Model. It's the core of every AI technology. Token is the most basic unit the model uses to handle data. Context is the total body of information the model receives each turn. You can think of it as the model's short-term memory. Context window represents the maximum number of tokens context can hold. Prompt is the specific instruction or question the user or system gives the model. It comes in 2 flavors, user prompt and system prompt. Tool is the function the model uses to sense and act on the outside world. MCP is the universal standard that unifies tool integration. With MCP, developers only have to follow one spec to build tools. Agent is the program that can plan on its own, call tools on its own, and keep running until it solves the user's problem. Agent skill is the specification document the agent reads. It mainly locks in the steps and rules for getting things done. Once you understand these concepts, you can make sense of any new AI product or technology out there. Whether it's Claude Code, Codex, Coworker, or OpenClaw, they all fundamentally run on this same framework. If this was helpful, don't forget to like and subscribe. I'm Alex. Hardcore Tech, explained in plain English. See you next time. Take care.